For years, the assumption seemed almost unshakable. If you wanted to manufacture advanced semiconductors at scale, sooner or later you would run into a wall built by someone else. Not a chip design wall, not a software wall, not even an equipment wall. A purity wall. And that's what makes this story so interesting, because the country that spent years being told it was dependent on foreign semiconductor technology has quietly achieved one of the most difficult manufacturing standards in the entire electronics industry, without importing the final solution from abroad. Most people never think about silicon wafers. They think about processors, graphics cards, AI accelerators, smartphones, the visible products. But every advanced chip begins as a polished disk of silicon so pure that describing it as clean almost feels inadequate. We're talking about impurity levels measured in parts per billion. In some stages, even smaller. A single microscopic defect can ruin a chip worth thousands of dollars. A contamination problem invisible to the human eye can destroy an entire production batch. For decades, mastering this level of purity wasn't just a manufacturing challenge. It became a gatekeeping mechanism. The companies that controlled the highest wafer standards controlled access to the upper floors of the semiconductor industry. And for a very long time, that club was remarkably small. American firms established many of the technical benchmarks. Japanese companies became dominant in ultra-high purity wafer production. European suppliers occupied critical parts of the equipment chain. Everyone else was playing catch-up, China included, which is why many analysts believed semiconductor sanctions would create a permanent bottleneck. The logic sounded reasonable. Restrict advanced lithography, restrict equipment, restrict specialized materials. Eventually, the entire system slows down. That was the theory. Reality turned out to be more complicated. Between 2020 and 2025, China didn't simply respond by increasing investment. That's the part everybody already knows. What happened beneath the headlines was more important. Companies across the semiconductor ecosystem started attacking hundreds of tiny dependencies simultaneously. One factory focused on crystal growth, another focused on polishing technologies. Others worked on defect inspection, specialty gases, ultra-pure chemicals, and wafer handling systems. Individually, none of these developments looked dramatic. Together, they started changing the equation. There's a tendency in technology discussions to focus only on the final product. It's like judging an aircraft solely by the cockpit, while ignoring the engines, fuel systems, and wings. Semiconductor manufacturing doesn't work that way. The supply chain behaves like a giant puzzle, where every piece matters, and silicon wafers sit at the center of that puzzle. A few years ago, many observers argued that wafer purity would remain one of China's hardest barriers. Not because the science was mysterious. The science has been understood for decades. The difficulty comes from consistency. Producing one perfect wafer is impressive. Producing millions of them with identical characteristics is an entirely different challenge. Industrial history is full of countries that mastered prototypes but struggled with mass production. Mass production is where engineering turns into discipline. This is where the story becomes difficult to ignore. Chinese manufacturers have reportedly reached purity and defect control levels that allow domestic wafers to compete in increasingly sophisticated semiconductor processes. Not everywhere, not across every node, not yet, but enough to change conversations that used to sound very different. And there's a broader question hiding underneath all this. What happens when a country stops importing not just products, but validation itself? Because the real power wasn't merely selling wafers. The real power was deciding what counted as acceptable quality in the first place. For decades, that authority sat largely outside China. Today, that assumption is facing a serious test. And strangely enough, the most important number in this entire story isn't a chip speed, a transistor count, or a market valuation. It's a purity threshold. We'll come back to that number. The easiest way to misunderstand semiconductor manufacturing is to imagine it as a race to build the most advanced chip. That's only the visible layer. Underneath sits an industrial ecosystem where tiny improvements compound over years until they become strategic advantages. Silicon wafers are a perfect example. The process begins with metallurgical-grade silicon, which is already around 98 to 99% pure. That sounds impressive until you realize semiconductor manufacturing requires purity levels approaching 99.9999999% and beyond. At that point, chemistry starts behaving less like manufacturing and more like obsession. Engineers grow massive single-crystal silicon ingots using methods refined over decades. These crystals are sliced into wafers thinner than a few sheets of paper stacked together, then polished until surface irregularities become almost impossible to measure. One particle, one defect, one inconsistency, and suddenly a chip factory producing billions of dollars worth of processors has a problem. That's why wafer production became one of the least glamorous but most valuable segments of the semiconductor chain. Nobody buys a silicon wafer because it's exciting. They buy it because failure is expensive. Historically, companies such as Shin-Etsu Chemical and Sumco in Japan built reputations around reliability that took decades to establish. Customers trusted them because every shipment behaved exactly as expected. Consistency became currency. And this brings us to the challenge China faced. The common narrative focused heavily on lithography machines from ASML, export controls from Washington, and advanced chip nodes. All important, but there was another question sitting quietly in the background. Could Chinese firms master the boring parts? Because history suggests that's usually where industrial power is won. Countries rarely dominate industries by achieving one spectacular breakthrough. They dominate by becoming dependable at thousands of small things simultaneously. That's harder. It's also less visible. One company worth paying attention to here is Shanghai Silicon Industry Group, often called SMIC. Long before semiconductor sanctions became headline news, the company was investing heavily in large-diameter silicon wafer production. Progress wasn't dramatic. Investors weren't cheering every quarter. There were years when advances looked incremental. Then the geopolitical environment changed. Suddenly, those incremental improvements mattered. A lot. Chinese chipmakers needed local suppliers capable of meeting increasingly demanding specifications. Wafer producers needed customers willing to test and adopt domestic alternatives. Equipment manufacturers needed feedback from both. A feedback loop began forming. Not overnight, not perfectly, but steadily. One reason many outside observers underestimated this process is because modern supply chains create an illusion. When a country imports a critical component for years, people start assuming dependency is permanent. It rarely is. Japan learned this lesson in electronics. South Korea learned it in memory chips. Taiwan learned it in semiconductor fabrication. China appears determined to learn it as well. There's also a subtle difference between invention and replication that often gets lost. Critics sometimes dismiss industrial catch-up by saying a country merely copied existing technology. That argument misses the point. Even when the destination is known, building the capability remains extraordinarily difficult. Everyone knows what a Formula One car looks like. That doesn't mean everyone can build one. The same principle applies to ultra-pure silicon wafers. The physics is public. The execution is brutal. And while American policymakers were focusing on restricting access to advanced technologies, Chinese industrial planners were pouring resources into material science, process control, manufacturing equipment, and talent development. The objective wasn't necessarily to surpass foreign suppliers immediately. It was to eliminate vulnerabilities. There's a difference. One strategy aims for dominance. The other aims for resilience. The second is often easier to achieve and sometimes more important. My own view is that many Western analysts initially evaluated China's semiconductor effort through the wrong lens. They looked for dramatic victories. The actual story was accumulation. Small gain after small gain, factory after factory, process after process, until one day a dependency that seemed permanent suddenly wasn't. And remember that purity threshold I mentioned earlier? The number itself matters, but the more important question is what happens after you reach it. Because achieving a standard is one thing. Turning that achievement into industrial leverage is something else entirely. And that's where the story takes an unexpected turn. Here's the twist. The story sounds like it's about China catching up. It isn't, at least not entirely. Because once a country reaches a critical industrial threshold, the conversation changes from, can they make it? To, what happens if they make enough of it? Those are very different questions. For years, global semiconductor supply chains operated under a relatively comfortable assumption. The most advanced technology came from a handful of countries, the most sophisticated manufacturing equipment came from another handful, and critical materials were concentrated among trusted suppliers. The system wasn't perfectly balanced, but it was predictable. Then geopolitics entered the room. Export controls expanded, technology restrictions tightened. Governments started talking about economic security with the same urgency they once reserved for military security. And suddenly, every nation discovered that supply chains are wonderful until they aren't. This is where China's wafer progress becomes more significant than the technical achievement itself. A domestic supply chain doesn't need to be better than the world's best to become strategically valuable. It only needs to be good enough. That's the reversal many people missed. The original assumption was that sanctions would create pressure by restricting access to advanced inputs. What actually happened is that pressure accelerated efforts to replace those inputs. Not everywhere, not immediately, but often enough to matter. There's a famous principle in economics. When access becomes uncertain, redundancy becomes attractive. Governments learn it, companies learn it, investors learn it. The semiconductor industry is learning it right now. Imagine you're a Chinese chip manufacturer. If your domestic wafer supplier can provide 90 or 95% of the quality you need with improving performance every year, the calculation starts changing, especially if foreign access carries geopolitical risk. Perfection becomes less important than predictability. That's an uncomfortable reality for countries that built their influence around technological leadership. Because technological influence isn't just about being the best, it's about remaining indispensable. Those are not the same thing. A supplier can lose some technical superiority and still remain essential. But once customers believe alternatives exist, even slightly weaker ones, leverage begins to erode. Slowly at first, then faster than expected. We've seen this pattern before. In the 1980s, American companies worried about Japanese electronics dominance. Later, Japanese firms worried about South Korean competitors. Then South Korea faced pressure from emerging Chinese manufacturers across multiple industries. Industrial history rarely stands still. Leadership changes hands more often than people realize, yet there is a strong counter-argument worth taking seriously. Many experts would correctly point out that achieving wafer purity standards does not automatically solve China's semiconductor challenges. And they're right. Advanced lithography remains difficult. Electronic design automation software still matters. Specialized manufacturing tools remain critical. Leading-edge chip production is an ecosystem, not a single technology. Anyone claiming otherwise is oversimplifying. But I think the counter-argument misses something important. Industrial independence doesn't arrive as a single breakthrough. It arrives as a reduction in vulnerabilities. One dependency removed, then another, until the overall system becomes far more resilient than outsiders expected. The question isn't whether China has solved every semiconductor challenge. Clearly it hasn't. The question is whether the list of unsolved challenges is shrinking. From where I sit, the answer appears to be yes. And there is a broader economic consequence here that affects ordinary people far beyond the semiconductor industry. Every modern product contains chips. Cars, medical equipment, industrial machinery, data centers, smartphones, even household appliances that somehow need software updates now. The more secure semiconductor supply chains become, the lower the risk of future disruptions that drive prices higher or delay production. That matters whether someone follows geopolitics or not, because semiconductor supply chains eventually show up in consumer prices. Always. The irony is difficult to ignore. A strategy designed to preserve technological advantages may have accelerated efforts to reduce dependency on those advantages. History occasionally enjoys that kind of symmetry. And the most revealing detail isn't the purity number itself. It's what Chinese companies started doing after reaching it. They stopped talking primarily about catching up. They started talking about scaling. That's a very different phase of the story. Remember that purity threshold from the beginning? The number mattered because it represented admission into a very exclusive club. A signal that a manufacturer could operate at a level once dominated by a small group of established suppliers. But after spending weeks reading production reports, industry data, and company announcements, I don't think that's the most important part of this story anymore. The important part is what comes after admission. Scale. For decades, the semiconductor industry rewarded specialization. One country designed chips, another supplied materials, someone else built manufacturing tools. The entire system became a masterpiece of efficiency. Efficiency, however, has a weakness. It assumes stability. When geopolitical relationships remain predictable, specialization works beautifully. When they don't, countries begin asking uncomfortable questions. What happens if access disappears? What happens if suppliers become unavailable? What happens if a critical technology suddenly becomes political? Those questions are shaping industrial policy from Washington to Brussels to Beijing. And they're changing corporate behavior as well. A semiconductor executive making decisions in 2026 thinks differently than one making decisions in 2016. 10 years ago, the primary objective was cost and performance. Today, resilience sits beside them in the boardroom. That shift may outlast any individual sanction package. Which brings us back to China. The achievement of high-purity silicon wafer production does not mean China has won the semiconductor race. I don't believe serious analysts would argue that. The frontier remains incredibly competitive. American firms still dominate critical software segments. Companies such as NVIDIA, AMD, and Qualcomm continue to lead in key areas of chip design. The Netherlands remains central through ASML. Japan maintains strengths in materials and equipment. Taiwan's TSMC remains one of the most important manufacturing companies on Earth. Those realities haven't vanished. What has changed is something more subtle. China's failure is no longer something competitors can simply assume. That's a major difference. A few years ago, discussions often centered on what China could not produce. Increasingly, the discussion revolves around how quickly remaining gaps can be narrowed. That isn't the same conversation, and conversations matter because investment follows expectations. If businesses believe a capability will eventually emerge, capital begins moving toward that outcome long before the final milestone is reached. There's also a lesson here for every country involved. Industrial strength isn't built during a crisis. A crisis merely reveals whether the work was already done. The factories, research centers, engineering talent, supplier relationships, and manufacturing discipline that produce these wafers weren't created overnight. They were accumulated over years, often with little public attention. By the time the achievement becomes visible, most of the real work is already finished. That's why I find this story fascinating. Not because it proves one side right or another side wrong. Not because it settles the semiconductor competition. It doesn't. What it demonstrates is that technological power rests on foundations most people never see. A polished disk of silicon, a defect rate measured in microscopic fractions, a manufacturing process so precise that success looks ordinary from the outside. And yet, entire industries depend on it. My prediction is fairly simple. Over the next decade, the semiconductor landscape will become less concentrated than it was during the previous one. Not fully fragmented, not completely independent, but more distributed. Countries have watched recent disruptions closely, and many reached the same conclusion. Dependence feels efficient until it becomes a risk. That's a powerful incentive. The irony is that a material most people will never hold in their hands may end up reshaping one of the most important technological competitions of the century. A silicon wafer doesn't look like power. Then again, neither did oil before people understood what it could do. If you enjoyed this analysis, subscribe and join me for the next one. There are plenty of stories hiding beneath the headlines, and they're usually more interesting than the headlines themselves. As for the wafer itself, it just sits there quietly, which is exactly how real industrial power tends to behave.